Our world is built on materials we pretty much take for granted every single day. But inside the most extreme places you can imagine, like, say, the heart of a nuclear reactor, the very steel holding it all together is in this constant, invisible battle. So today, we're going to uncover the hidden science that keeps that steel from, well, failing.
Just think about that for a second. It's a terrifying thought, right? Under the insane conditions inside a reactor, the materials that are specifically designed for strength can become dangerously fragile. And this isn't just some hypothetical question, it's a critical challenge that scientists are working to solve right now.
So the material we're talking about is a specialized alloy called 9Cr 1Mo steel. It gets picked for jobs like this because of its incredible strength and resistance to heat, but it has a hidden weakness. Over time, and especially when temperatures drop, it can change from a tough, forgiving material into something that could fail, catastrophically.
Okay, so to really get the risk here, we need to talk about two key properties: ductile versus brittle. A ductile material, think of a paperclip, it'll bend and stretch, giving you a really clear warning before it actually fails. But a brittle material, like an icicle, just snaps, no warning. In a nuclear reactor, you want ductile. You absolutely positively cannot have brittle.
And that tipping point, the specific temperature where steel goes from tough to fragile, actually has a name. It's the ductile-to-brittle transition temperature, or DBTT for short. Now, for safety, the whole game is to push this temperature as low as humanly possible, way down into a temperature range the reactor will just never experience. So, how do you do that?
Well, a team of researchers decided to find the perfect recipe for this steel. The whole idea was to use a super precise heat treatment process before the steel is ever put to use. Basically, they wanted to bake in the toughness by refining its internal structure right from the start.
The process itself has three main stages, but the crucial variable, the secret ingredient they really wanted to test, was the temperature in that very first step, austenizing. So they cooked up 3 different batches, each one with a different starting temperature.
First up in our little metallurgical bake-off is a sample treated at 950 degrees Celsius. We'll call this our low-heat contender. Is the gentle approach going to create the toughest steel? Let's see.
Next, candidate number 2 gets a little more heat. This one's taken all the way up to 1025 degrees Celsius. This is our medium heat option, right smack in the middle.
And finally, our third candidate is pushed to a blistering 1100 degrees Celsius, our high heat challenger. So we've got 3 totally distinct recipes. Now it's time to find out which one can really take a punch.
All right, once the samples were all prepared, they had to face the ultimate test of toughness. It's a standardized and frankly brutal exam known as the Sharpie Impact Test. This is where we separate the truly tough from the dangerously brittle.
Okay, just picture a massive, heavy pendulum. It swings down and wham! It smashes right through a small, notched sample of our steel. The machine measures exactly how much energy that little sample absorbed before it broke. The more energy it soaks up, the tougher the material. It's simple, super effective, and totally decisive.
And the results are in. And wow, they are crystal clear. The winner, with the lowest DBT of a very chilly -58 degrees Celsius, was the 1025 degrees sample. That is way better than the others. In fact, the hardest sample was actually the worst performer of the bunch. Our medium heat recipe is the champion.
And this is so cool, because this shows you exactly what's happening on a microscopic level. On the left, that's the brittle fracture. See how it's a clean, flat break? That's called cleavage. Very little energy gets absorbed there. But on the right, that's the ductile fracture. It looks like torn metal, full of these little dimples where the material stretched and ripped, absorbing a ton of energy in the process. That is the safe failure we want to see.
So, the 1025 degrees sample was the clear winner. But in science, the most important question is always, why? To figure that out, the researchers had to go from that big impact test down into the tiny, microscopic world inside the steel itself.
You see, a core principle in metallurgy is that a finer internal structure, what they call grain size, is usually a lot better. Just think of it like a brick wall. A wall made of small, tightly packed bricks is way stronger and harder to crack than a wall made of just a few giant, clunky blocks. A crack has to keep changing direction at every single grain boundary, and that just eats up energy and stops it in its tracks. And would you look at that? When we look at the images, you can see the heat treatment worked like a charm. On the left is the steel as it was received, with these big, stretched-out grains. And on the right, That's our winning 1025-degree sample. The structure is so much finer, so much more uniform. It is a much, much better brick wall.
And this is where the story gets really interesting. Because if the rule of thumb is smaller grains are better, then you'd totally expect the sample with the absolute smallest grains to have won the toughness test, right? Well, that's not what happened.
When the researchers actually measured the grain sizes, they found a bit of a surprise. The 950-degree sample, the one that came in second place for toughness, it actually had the finest grains. Our champion, the 1025-degree sample, had slightly larger grains. So this kind of flies in the face of that simple smaller is better rule. What is really going on here?
Well, it turns out that toughness isn't just about one single property. It's a really delicate balancing act. It's like the story of Goldilocks, right? You don't want things too hot or too cold, too hard or too soft. You want them just right. And there was another piece to this puzzle.
And here it is. Hardness. See, that 950-degree sample with its superfine grains was also the hardest material of the three. And here's a key thing to remember. Hardness and toughness are not the same thing. Something that's really hard can also be really brittle because it has no give. It might resist getting scratched, but it could shatter if you hit it hard enough.
So here it is, the winning combination. The 1025-degree sample had grains that were fine enough to make it really hard for a crack to spread. But at the same time, its internal structure was also a little bit softer and less rigid than the 950-degree sample. And that little bit of softness allowed it to deform on a tiny microscopic level, absorbing energy like a shock absorber before it even thought about breaking. It had the perfect balance.
And hey, don't just take my word for it. The researchers themselves summed it up perfectly. The winner had the, quote, optimum combination of fine grains and slightly less strength, or a softer matrix. It wasn't the absolute best in any one category, but it was the best overall. It's the Goldilocks principle in action.
This whole process is just a fantastic reminder of the incredible and often completely invisible science that's at work all around us. Finding the perfect recipe for steel isn't about pushing one property to its absolute max. It's about a deep, deep understanding of the trade-offs to get that perfect, safest balance. Which kind of makes you wonder, right? What other hidden discoveries like this are quietly making our world stronger and safer every single day?